right, to start with the introducing the derivative and kind of going, we need to do one little tiny review. And that is the review of the equation of a line. All right. So if you recall, forms of an equation of a line. We have what we call standard form. And standard form is your ax plus by equals c. All right. So we talk about if math lab or anything asked you to put an equation in standard form, this is what they mean. All right. When we do this, the a value is always greater than 0. So if your ax term is negative, switch everything to the other side of the equation so the ax term is positive. That's your standard form of a line, the equation of a line. You are probably most familiar with your slope intercept form. And what is your slope intercept form? When you think of an equation of a line, it should be what comes to your head. What is it? Yeah. And that's often how you can give your answers if you're being asked for an equation of a line. Of course, m is the slope and b is y-intercept. Now, very often, though, there's a third one. This is the one I tend to forget about a little bit, but this is the one we need to use, which is why we're doing this. Very often, or in general, you need two things to write an equation of a line. You have to know the slope of the equation to write an equation of a line. You also need at least one point that equation goes through. So as long as you have one point anywhere that you know that equation goes through, and you have the slope, you can write the equation of a line in what is the point slope form. Your slope intercept form is just a special case of the point slope form, and the one point it uses is the y-intercept, which is 0, b. So the point slope form itself looks like this. Okay, where x and y, x1, y1, is a point on the line. Okay, so here's the deal. Quick example. Because ultimately what we are going to be doing today is finding these equations of a line. And I want to make sure you know how to do this part of the problem, which is kind of the last step. So if you have a slope of -3 and a point of 5, 2, so you know a point, you know a slope, you should be able to get an equation of a line. How you want to start is with your y minus y sub 1 m, okay, and you plug in what you need. So my point is 5, 2. So you start with y minus what goes in for y sub 1. 2. Slope's -3, x minus 5. And I'm just going to have you turn these into y equals mx plus b for consistency. Math, when you're doing the math lab problems, just read the problem very carefully. They will tell you how they want the final form. So you know what standard looks like, you know, slope intercept, or you might be able to leave it in this form. But normally we go ahead and we work this out, and we all know how to do that. And to solve for y, it just looks like this. Add 2, 17, right? Look good? Please check me for mistakes. Yes. Hmm? You want to start from here? Oh, if it's standard form, then when you kind of get to this point here, or actually no. The only thing you have to be careful with standard form, when you're putting standard form together, is the x term has to be positive. So do you see where this negative is negative? So we want to move that to the other side. So that dictates where to move everything. So to do standard form, the 3x has to come over. So to do standard form, it would be 3x, right, plus y minus 2. So it would be 3x. Make sense? Okay, that's the only thing. When putting things in standard form, just that x term has to be positive and has to come first. Okay? So if you moved everything to the other side, you just have to flip it. So this is your standard, and that's your slope intercept. Okay? So why do we need an equation of a line? And why is it important to get an equation of a line? So let's draw something that a graph we're all very familiar with, just for picture purposes. We'll draw this graph. So we have this nice parabola, right? And that's our function. So it doesn't matter what the equation is, we'll just call it f of x. We can draw tangent lines, right? Anywhere across this line. So I can come over here and draw a tangent line at A. Everybody see that? I can set a point B and draw a tangent line at B. Okay. I can set a point C and draw a tangent line at C. Do you see all those 3 tangent lines? Aren't those 3 lines all going to have different slopes? The slope of the tangent line to a function is your derivative. That's all a derivative is. It's the slope at a particular point on a graph. That's it. Okay, so a derivative is a slope. It's a remember, and this is what you want to think about. A slope is a rate of change. A derivative is a rate of change that's occurring. Now, that derivative is going to change where if you change along the equation, correct? The f of x. All right, it's not going to be the same. It's going to be different at every point on your f of x. Yes. Perfect. So if you think about it, how did we get that? This is just like how we started limits in 2.1 and we found instantaneous speed versus average. So let's take a look at that. I'll draw a second graph. I'm just going to do a parabola. They're just easy to draw, and they're good to use for now. We're going to use all kinds of functions that aren't parabolas. And I'm going to go, all right, suppose I wanted to know what that tangent line was right there, with that slope right there. Is why I didn't know, I couldn't figure that out. I wouldn't be able to, without a point, right? So if you were just told, hey, what's the derivative at A? Without another point, you can't come up with the equation of a line. You can't get much information. So what we did before is we said, hey, we'll start by finding first, right? Didn't we do average velocity? Okay. And then what did we do with that B value? We moved it closer and closer, correct? We went and said, all right, I'm going to put point here. I'm getting really, really close. And as it moves closer and closer, I will eventually get what I want, which is that. So what I want to do is use the idea of a limit. And this is how I want to do it. Since this B value is changing, right? Everybody see that? A staying constant, because that's the one I want. But that B value is going to move. So instead of calling it B, I'm going to do one more picture. I'm going to refer to that distance instead of the point. And I'm going to call that distance h. All right? So if I call that distance h, what's this point over here then? It's A. Yep, that's going to be A plus h. You agree with that? All right? Now, to do a slope, you know we need a change in y over a change in x, correct? So I not only need my x values, I need my y values. So let's come over here. Well, whatever my function is, this is f of a, correct? And then this one would be f of what? A plus h. All right, so let's if I were to find the slope, wouldn't it just be, so the slope of the secant line, not the tangent, because this is between the 2 points, well, the slope of the secant is simply what? F everybody say it? Minus, because change in y, minus what? Over, well, what's this point here? Well, we can clean this up a little bit, can't we? We can definitely clean this up a little bit. Oh, so the slope of the secant line is f of whatever a plus h is minus f of whatever a is, whatever point we're picking to do this on, over h, correct? All right. I don't want the slope of the secant line, though. What do I want? I want the slope of the tangent line at A. You just did a whole unit on limits. In other words, I want that h value to get smaller and smaller and smaller, correct? To the point, if h became 0, wouldn't I be right at A? So what do I need to use when I want to approach 0? A limit. Does everybody see what I'm trying to do? It's kind of what you did numerically in the very first class. You took values like 0.0001, you know, remember? And you went closer and closer and closer. We're going to do it, but we're going to use our limit function because we don't want to sit there and calculate a bunch of values numerically anymore. So what we're going to do is, hey, I want to take this entire thing here, f of a plus h minus f of a, and I want to take the limit of it as h itself goes to 0. Because when h becomes 0, we're right there at A. So this formula actually represents the rate of change. There's another better definition. It's the derivative at a point. I don't always like the way they write everything in the book. Hold on. Yeah. This formula right here represents, it's the definition of the derivative of a function at a point. The point is A. And we represent derivative. There's a lot of different notations we're going to use for derivative. When we talk about the derivative at a point, we're going to call it f prime of A. So f prime is one of the notations we are going to use for derivatives. And we have to put one little caveat on there because we have to make sure that f prime of A actually exists. Okay, so we will get into situations where derivatives will not exist. So we'll get to that later. But right now we're going to say if f prime of A does exist, and you can find it, then we say f is differentiable at A. You've actually done this before in pre-calculus. It was called a difference quotient. Do you remember doing something like this in pre-calc? Okay, if you took pre-calc 1 not too long ago, you worked with something called a difference quotient, right? So this is very specific though. This is finding the derivative at a particular point. We're going to generalize this next, but right now let's just focus on that point and let's do an example. So let's suppose to make sure we all know how to use this. And you'll see real quick why we don't want to do this all the time. It gets a little algebra crazy in some cases. This one's not too bad. So we want to use, we call this the limit definition of a derivative. So anytime you see the word limit definition of a derivative, you actually have to use this formula. So we are going to use the limit definition of a derivative to compute, and I'm going to take it one step further. I don't even want just the slope. I want to compute the entire tangent line because you can find the slope and then you can also find the tangent line. To compute the tangent line at x equaling 2. All right, but before we can do anything, we do have to find the slope because to find any equation of a line, you need a slope. So let's do that first. So you start with your definition. I want the limit. So to find the slope of that, oh, wait, it's coming back. It really is. There you go. To find the limit, to find the slope, we're going to take the limit as h approaches 0. All right. You got that formula. There it is in the upper corner. So now I want f of a plus h. Now here's the good news. because you know what A actually is, we can use A for our X value. What is our A? At what point are we looking at when X is what? Yeah, since X is 2, that means your A is 2. So we can kind of shortcut this and say, well, I want to do it when A equals 2. So the first thing I need is what is, and I'm going to do it off to the side first, A, sorry, not A, I'm going to use 2. What does 2 plus H look like in that formula? What does it look like? Because my f of x is 2x squared minus 5. I want to find f of 2 plus h, right? So I want 2 plus h squared minus 5. Does that make sense? To get my f of a plus h, in this particular problem, my a is 2, I need f of 2 plus h. So I need this. Well, I'm going to clean, I like to clean things up on the side first before I put them in the problem. So let's work, we have to work that out. What does that come out to? That's 2. What's 2 plus h squared? Do you know how to quickly square a binomial? If you don't, you will, because you have to square binomials a lot. So let's square the binomial. Quick process to square the binomial. Square the first term, what do you get? Multiply the 2 together and double it. Because when you square it, you end up with 2 of those terms. So what's 2 times h? 2h. What's that doubled? Plus h squared. That's how you square a binomial. Minus 5. I'm going to continue cleaning it up because I just don't like to do it in the problem itself because it gets really messy. All right, so what's that? That's 8 plus 8h minus 2h squared minus 5. So what do we get here? 8h minus 2h squared. 8 minus 5, 3. Right? Does that look good? Did I do any mistakes? Make sure I didn't make any mathematical errors. What did I do? I don't know where the minus, that's why I said check what I did. Yeah, I don't know why I switched to minus, right? Is that better? You like that better? Okay, good. It is 8 minus 5 though, yes. 3. All right, so I'm gonna put that in. 8h plus 2h squared plus 3. Now go back to your formula. We only did this piece. There, y'all see that? What do we need? Minus, we need an f of a. Let's do that off to the side also. So not only do we need f of 2 plus h, we need to know what f of, I don't know why I put 8, sounds like a. F of a, which is f of 2, correct? We need f of a. That's 2 times 2 squared minus 5. It's 3. Everyone agree? Okay, so your original formula is this minus the f of a. Minus 3. And what's in the denominator? Simply h. Okay, can I take h to 0 yet? No, what happens if I plug in 0? It doesn't work, but we know we can algebraically simplify things first, can I? Let's try algebraically. So one of the things you said, remember, when we do a limit, you always try just plugging in your 0 first, or whatever you're taking the limit to. In this case, h is going to 0. You try to do that first, but if it doesn't work, you massage your function a little bit. So let's do that. So it's still the limit as h goes to 0. Well, 3 minus 3 cancels out, correct? What do I have left? I'm not going to write it yet. I have 8h plus 2h squared. What can I factor. That's the big key here. What can I factor out of that? I can factor out a 2h. Right? So what does that give me? 4 plus h? We go with 4 plus h. Oh, what happens to my h's now? Yeah, you can cancel them. So this is going to be key. If you can't cancel your h's, you're not going to be able to do your limit. In every single one of these problems you do, you will somehow, if you do the correct algebra, be able to cancel your h's. That's how you know you're on the right track. Because when that h cancels, you're like, must be doing this right. Okay? All right, so what I really want now is the limit. Oh. What's the answer? Yes. What's the answer now? It's 8. I just didn't write it. It's 8. So remember, that means the slope is 8. The slope is 8, yes. Oh.
I did 8 plus 2h and ended up being the same thing.
Oh, you mean if you didn't factor you just didn't factor the 2 out, but you factored the h out. You did. Yeah, if you didn't factor the 2 out, that's fine. The key is at some point your h's will cancel, because you can see in all of, even when we generalize them to an x, we're doing a specific point. We're going to do a general in a little bit. Your h should cancel. Sometimes it's factoring. Do you think it's going to be factoring all the time? Sometimes we're going to deal with radicals and you're going to use a conjugate. Okay, the same tricks you did with limits are the same tricks, algebraic manipulations you're going to do here for these problems. So if we were just, and this is where you want to be careful in Math Lab when you're doing those problems. If you're just asked for the slope at that point, you're done. Whatever function this is, it's an x squared function, correct? The original function, yeah. So it's a parabola. At x equaling 2, the tangent line is going to have a very steep positive slope of 8. All right. To get the actual tangent line, you need a point. You can get a point looking at the original by knowing you want the x value to be 2. Okay. So what is the corresponding y when x is 2? So what's f of 2? 3. Yeah, it's going to be 3. So this is at the point 2, 3. So you can use the 8 and use the 3 if you're asked to come up with the equation of a line. Sometimes you're going to be asked for slope, and that's fine. Sometimes you're going to be asked for equation of a line, in which case then you got to finish with y minus 3 equals 8 times x minus 2. Right? And then it's just... watch my math. Make sure it's correct. (13) minus, why did I put plus? Minus, we go with minus 13? I can't find my eraser quick enough. Pretend I didn't do that. Are we good? I think we're good with that equation. So there's your slope, but there's your equation of the tangent line at that point. Okay? These are nice. Defining it at a specific point actually makes the work a little easier, but here's the problem. I only found the derivative at that particular point. If I want another point on the same graph, suppose I don't want x equals 2. I want the derivative at x equals 10 for that function. What do I have to do? Whole process over again, correct? So what we want to do instead of finding it at a point it's better to find a general function. All right, and that's what we're going to do. Instead of finding it at a particular point, we're going to go ahead and find a general function. All right, I want to make these videos a little shorter, so I'm going to stop this one and just start up another one real quick because this takes us into 3.2.